Hello friends, in the previous video we have seen theory related to stresses in beams. In this video we will see the different numerical on stresses in beams. See the first type of numerical, that is to find the stress at extreme fiber. Type 2, to find moment of resistance and loading on the beam. Type 3, that is beam subjected to both hogging and sagging bending moment. Type 4, design of the beam. Type 5, that is strength of beam. Type 6, that is plates are placed at vertical faces. Type 7, that is plates are placed at bottom and top side of the beam. Type 8, that is numerical on unsymmetrical bending. See, to solve this problem, we should use different formulas. See, you can see the summary of important formulas. Already I explained all the things in theory part. See, to find the position of neutral axis, you can see this is the y bar. Y bar is equal to summation of A into Y upon summation of area. Next, step 2 is to find the moment of inertia. Then step 3, find the depth of compression and tension side about neutral axis. For simply supported beam, below neutral axis, that is tension, that is YT, that is very important type. Part of tension, YT, very important part. Next, above neutral axis, for simply supported beam, compression will be there, that is YC. For cantilever case, below neutral axis, it's a compression. Above neutral axis, that is tension, you can see YC and YT. Stress in the beam using flexural formula, we know that structural formula is equal to M by I is equal to sigma B by Y is equal to E by R. Force acting on each side, we know that compression force is equal to area of cross section in compression into average compressive stress. Tensile force is nothing but area of cross section in tension into average tensile stress. See, for type 1, that is find the stress at extreme fiber. Here, for example, we are taking first problem. Find the section modulus for the T section as given in mm. You can see this is a T section. Already in the moment of inertia, we covered different sections. This one is the T section. You can see this is the vertical rectangle. Dimension base, that is 20, depth, that is 100. Here for this horizontal rectangle, dimensions base 100 and depth, that is 20. Here you have to find out Z, that is sectional modulus. We know that position of neutral axis, first of all we have to find out by using the formula of Y bar. Y bar is equal to A1 Y1 plus A2 Y2 upon A1 plus A2. So here we have to calculate area 1, that is 20 into 100, and area 2 is also 20 into 100. So we have the value of A1 and A2, that is 2000 mm square. A2 is also 2000 mm square. We can find out the value of Y1 already in the center of gravity in the centroid. We know that how to calculate distance Y1 and Y2. Here the distance Y1 is equal to 50 mm and Y2 is equal to this 100 plus 20 by 2, that is 110 mm. We have taken this base as a x-axis, so we have the value of Y1 and Y2. Now we have the value of area 1, area 2, Y1 and Y2. We can calculate y bar by using formula a1 into y1 plus a2 into y2 upon a1 plus a2 is equal to 2000 into 50 plus 2000 into 110 upon 4000 is equal to 80 mm. Means from baseline, the y bar will be at 80 distance. Here, the y bar will be at a distance of 80. So to calculate sectional modulus, we have the formula zxx is equal to ixx upon y bar and zyy is equal to izz upon x bar. So first of all, we have to calculate ixx by using the moment of inertia about xx. It is moment of inertia ixx is equal to ixx1 plus ixx2. Already we know that how to use parallel axis theorem. By using parallel axis theorem, we can calculate ixx. The formula for ixx1 is ig1 plus a1 h1 square plus ig2 plus a2 h2 square. We know that ig for rectangle, that is base into d cube by 12 plus we have the area, and h1 is nothing but difference between y bar and y. So here y bar is 80, 80 minus 50 whole bracket square. Here you can see the difference between y bar and y. For second rectangle, the value of y, that is 110 minus 80, 80 is the y bar. Remaining things are same as previous. So the value of ixx is equal to 5.327 into 10 raised to 6. Now we know that moment of inertia about y axis, Iyy is equal to Iyy1 plus Iyy2. Here not need to use parallel axis theorem because diagram is symmetrical about vertical center line. So the x bar will be 0. So not need to use parallel axis theorem while calculating Iyy1 plus Iyy2. So here formula will be db cube by 12, db cube by 12. So answer will be 1.733 into 10 raised to minus 6 mm raised to 4. Now we have the value of ixx and we have the value of Iyy. Here you can do the necessary correction. Instead of Izz, there is a Iyy. So zxx is equal to ixx upon y bar. We have the value of y bar, that is 80. Here suppose you are considering this horizontal line, this vertical line as a x-axis, then x bar will be 100 by 2, that is 50. So here we have the value of x bar, that is 50. Here this one is Iyy. So we have the value of ixx and y bar. Here we have the value of Iyy upon x bar. So the answer will be zxx is equal to 69.087 into 10 raised to 3 mm cube. Unit is very important. And zyy is equal to 34.67 into 10 raised to 3 mm cube. See, this is the very important problem. Just we have to calculate the section modulus. To calculate section modulus, you have to calculate y bar and x bar. Then moment of inertia about xx. Then sectional modulus is equal to, we have the formula ixx upon y bar, Iyy upon x bar. You can find out the values. In the next video, we will see another problem. Thank you. Thank you very much.